Using mathematical induction, we're going to prove that the sum of the square numbers is equal to this. So first we start with step 1, which is when n is equal to 1. And in that case, the left-hand side is equal to the sum from r equals 1 up to 1 of r squared, which is 1 squared, which is 1. The right-hand side is equal to 1 times 1 plus 1 times 2 times 1 plus 1, all over 6. Oh, let's fix that quickly. All over 6, there you go. That's 1 times 2 times 3 over 6, which is equal to 1. Therefore, the statement holds when n is equal to 1. So the base case is true. Now we move on to step 2. Step 2 is when n is equal to k, our assumption. So we're going to assume that the sum of r equals 1 up to k of r squared is equal to k plus 1, 2k plus 1, all over 6. And that's our assumption. Now we move on to step 3. Step 3, our inductive step, is when n is equal to k plus 1. What we want to show is that the sum from r equals 1 up to k plus 1 of r squared is equal to, well, k is going to become k plus 1. K plus 1 becomes k plus 2 because it's k plus 1 plus 1. So that's going to become k plus 2. And the last bracket is 2 times k plus 1 plus 1, all over 6. Now this last bracket is going to simplify a little bit. We can expand this to get 2k plus 2 plus 1, so 2k plus 3. So I'm just going to simplify that down to 2k plus 3. Starting with our left-hand side, this is going to be equal to the sum from r equals 1 up to k of r squared, so the first k terms, plus the k plus 1 term. And the k plus 1 term is k plus 1 squared. Now we're going to make our substitution. This we know from our assumption is equal to this. So it's k plus 1, 2k plus 1, all over 6. And then on the end we've got plus k plus 1 squared. Now we could expand this out all out, but I'm going to factorize something out. I know at the end I want to have a k plus 1 over 6. So I'm going to factorize out k plus 1 over 6. In this blue bit here, what do I have left? Well, I've got the k plus 1 over 6, so what I have left is a k and a 2k plus 1. And here, I've got a k plus 1 over 6, and I need a k plus 1 squared, so I need an extra k plus 1. And I also need to multiply that by 6, so that those 6's will cancel to give me just one of those k plus 1 squareds. So I've got k plus 1 over 6 out the front, and then a bracket. And now I'm going to expand and simplify. That's 2k squared plus k plus 6k plus 6. And then I need to factorize in. Oh, not sure what happened there. Let's try writing that again. There we go. K plus 1 over 6. Factorizing this expression here, 2k squared plus 7k plus 6. Well, I know that's going to be 2k. And I know there's going to be a k to get the 2k squared. To get 6, it's either going to be 2 and 3 or 6 and 1. Probably going to be 2 and 3. And 2 times 2 would be 4, plus the 3 would give me the 7. So I need 2 and 3, which actually is equal to what I wanted. Now, in this case, we actually could have used our want to show to do that factorizing step for us, because we know we want it to be k plus 2, 2k plus 3. So we could expand that and see that it gives us this expression. And it can help us work that way. So using a little bit of knowing where we want to get to helps us get to where we want. And that is equal to the right-hand side in a slightly different order, but it's the same thing. As always, we must not forget our step 4 for any proof by induction. We must always finish with our concluding statement. And our concluding statement says that, hence by mathematical induction, since the statement holds for n equals 1, and if it holds for n equals k, it also holds for n equals k plus 1, it must be true for all positive integers.